Okay guys, welcome back to Form 5. The next part of our chapter number 4 will be understanding of a semiconductor diode. Okay, so that is 4.2 semiconductor diodes. Okay, semiconductor diodes. So from the word itself, very clear. Before we can understand how a diode functions, we need to look at the semiconductor. So what is semiconductor? Example of semiconductor. Okay. Okay. First, we look at semiconductor. Number one, element. In our periodic table, we have 100 plus element, but there are a few that has a characteristic of semiconductor. We look at a few that is very famous. Okay, we have silicon. Okay, we have silicon. This one is the most abundant on the surface of the earth, which we use it most of the time. And then we have germanium. Okay, germanium is quite scarce. I mean, we don't have that much germanium, so that's why it's very expensive. But it's actually a much higher quality semiconductor rather than silicon. It's because of the sensitivity of the germanium. And of course, carbon is also falling to the same group. But carbon is not a very reliable semiconductor. It's good for something else other than a semiconductor. So first, we choose only this one. Okay, we only discuss this one, but not this one, not this one. Definitely not carbon. Okay, carbon is totally out. We have two types of very famous semiconductor materials, silicon and germanium. A lot of the things in the market are made of silicon actually. Okay, unless maybe you need a very high sensitivity equipment like satellite. Okay, high-tech military device, high-tech communication device, okay, and so on. Then we use germanium because they are actually quite expensive and they are more sensitive. But for now, our normal usage, silicon is actually good enough. Okay, so we look at silicon. Okay, the element silicon. Now it is called semiconductor because it has a conductivity. Okay, a conductivity. Conductivity means how well it conduct electricity. This conductivity of semiconductor is in between insulator and conductor. Okay, that means it's better than insulator, but it's less than conductor. Somewhere in between that is called semiconductor. For the job of it, you can also call it semi-insulator, but I don't think you'll get any marks for that in your exam. So conductor has a conductivity, semiconductor have a conductivity of between insulator and conductor. That's why it's called in between, material in between. So it's a semiconductor. So first we look at why is semiconductor so important. Okay. First, we need to know is the structure of silicon. So silicon have a symbol of Si. So here we draw some of the silicon structure. Okay, a few of them. I think 3 is enough. Okay, here already one row. Another row here. Another row here. And another row here. So we have, okay, we make it 4 rows each. Yeah, one more row down here. So for each, so each cross section, each intercept here is representing a location of silicon. Okay, so this is these are all our silicon atoms. Okay, silicon atoms, silicon atoms. Okay, so they are all Si. Silicon symbol is Si. Okay, Si. Well, I like doing this job. Just simply writing down. No need to talk so much. Okay, silicon. Well, silicon is a quartet. Quartet means it has 4 electrons. And as you know, 4 is actually not stable. Okay, 4 is not stable in a periodic table. So if you want to know, if you look at the periodic table, the last one, I think I have the periodic table. You wait for 30 seconds. Here comes my periodic table. So if you look at the last row, this is the one with what we call it, group 4. This is a carbon, silicon, germanium, stannum is tin, plumbum. Okay, and then don't know what the heck is this, unoquadium. Okay, whatever, forget about that. That one's going to give you nightmare. You have this group are actually the, what we call it, the silicon group. Okay, silicon group. Sorry, not silicon group, the semiconductor group. Now, the most stable one will be here. If you look at this carefully, these are the most stable one: helium, neon, argon, krypton, xenon, and this radon. Well, of course, if you look at the last one, okay, they have this similarity. You want your element to be stable, or any chemical reaction to be stable, if the best is you have 8 electron at outside the orbit. Outer shell is 8 electron. So silicon only have 4. So why is silicon so stable? The reason is very simple, because each of these silicon, they share with another 4 silicon atom around them. So that means this one here is going to share like this. Okay, share like this, so that virtually this silicon has actually 1, 2, 3, 4, 5, 6, 7, 8 electron around them. So it make it very stable. So it's not only happen here, it happened throughout the whole structure. Okay, it happened throughout the whole structure, where all the silicon nearby will be sharing their electron with their neighboring silicon atom. Okay, neighboring silicon atom. So in this case, it's going to share here. So they are very stable. Okay, they are very stable since they share with all their neighbor, with their brotherhood there. Okay, so here, this one also. Okay, so that is why silicon is stable, simply because of this type of structure. So that means each silicon atom share, okay, each silicon atom share 4 electrons from its neighbor. Okay, from its neighboring silicon atom. Okay, from its neighboring silicon atom, to make it so stable. But important thing is pure. This is pure silicon. Pure silicon is actually useless. Then why we talk about semiconductor in the first place? It is useless in a pure form. We need it to be useful only when it comes to unpure form. Okay, not pure silicon. Pure silicon is useless, so we have to make it unpure. All right. So to make it unpure, we have a process called doping process. Okay, that's where we come to our doping process to make the silicon become very important. Okay, the doping process. We don't look at the process in detail, but we need to know at least something, what thing they put in to make it become so, what we call it, to make it become so accurate, so useful. All right. Now, doping means introduction. Okay, introducing some other impurity. Okay, some other impurity into the pure silicon. Okay, it happened to germanium also, but we are talking about silicon, so I only write pure silicon here. So we're introducing some other impurity into the pure silicon, and then the impurity are different type of atoms. Okay, the impurity are different type of atoms, okay, with almost the same size. It cannot be too big. Okay? It cannot be too big. You cannot introduce hydrogen into silicon. Okay? It don't work that way. You also cannot introduce uranium into silicon. Okay? Maybe there are chemical processes that can happen, but it does not work that way. Okay, so the size are too big or either too small. So we need something that is very near to the size of the atom of silicon, so that we don't really change the physical appearance of the silicon. All right. So now doping process, we have two types of doping process. Okay. First, we call positively doped process. Okay. The first one is positively doped, okay, silicon. Okay, positively doped silicon. So this positively doped silicon will make the silicon become a little bit positive. So this positively doped silicon is called the P-type. P-type silicon. Okay, P-type silicon. So now we're going to look at the P-type silicon. So here we only draw 3 rows, so this is not really that complicated here. Alright, so now we have this silicon atom. Okay, initially they are all pure silicon atom. Okay, so that means, as I said just now, is useless, and then each of them have shared their electron with a 4 neighboring, okay, atoms, silicon atoms. All right, so this drawing, each line represent each one of the sharing, so like that. Okay, of course the other side here they are also sharing, except we don't draw every atom, like we got no time for that. And then here also same thing. Okay, so now they are okay, they are actually very stable. We're going to disturb them by the process of doping. We will replace one of the atom here. Okay, because this one has 4, you want to make it slightly positive, you need to reduce the number of electrons. So one of the silicon atom will be replaced by a type of atom that has only 3 electrons outside. Okay, only 3 electrons outside. That type of atom is called trivalent atom. Okay, trivalent. Example of trivalent atom are boron. Okay, boron, arsenic. Sorry, boron, indium, and gallium. Okay. Example of trivalent, okay, trivalent atoms are boron, indium, and gallium. Okay, and gallium. You can remember them as BIG, big. Very easy to remember. So let's say we use boron. Okay, we put boron there, B. So now this boron have only 3 electrons outside. So that means by replacing one of the atom here with boron, you lose 1 electron, because this boron only has 3. Okay, only have 3 electron outside. So it only can share 3. So that means this one are completed except here. Okay. So this one here, you're going to lose 1 connection. You only have 1 with a neighboring, but 1 is missing here. This missing 1 is a place where it needs electron. So this place is called hole. Okay, hole is not something physical, but it is a place, a location where it will attract electron. So if it will attract electron, it seems a little bit positive here. Okay, so that's why it's called a hole. It's actually nothing there. It's not a particle. It's just simply an emptiness that have a potential to attract negative charge, electron. Okay, electron. Well, this method is called S-type. P-type. So this P-type semiconductor is because for every million of silicon, we replace one boron. The ratio had to be very specific, okay? The ratio had to be very specific. Now, more about this is that even though we say that it is positive, but there are still some other thing inside there that can carry the current. So, in a p-type, okay, the characteristic of p-type silicon or p-type semiconductor, number one, the majority charge carrier. The majority charge carrier is the hole. Okay, are the holes. Most of the current carry inside this p-type or the positively doped silicon are holes. Okay, and then number two, the minority charge carrier are the free electron. Okay, are all the free electron. So remember, hole and free electron. The hole normally you can use a symbol H, and the free electron we can use a symbol E. Sometimes to be more specific, we can put H positive and E negative to represent the difference between them, between the charge. Alright, so that is a characteristic of the p-type silicon. Okay, p-type silicon or p-type semiconductor. Other types of semiconductor are also producing p-type like that, doing the same thing. We call doping process. Okay, so that is our we call the doping for the positive type. Now we come to the negative type. Okay, the second one is our negatively doped silicon or semiconductor. Okay, the negatively doped. So we call this one the N-type. Okay, the N-type silicon. So the N-type silicon have the same characteristic, except the way we do it is slightly different. So how do we do it in the first place? Just now you put a trivalent, right? Because you want to have less electron. So now the difference of N-type compared to the P-type is we want something that have more electron compared to silicon. Okay, so our silicon, we have this completed structure which is very stable. We call that one the 8 electron outside the outer shell. So that one complete, pure, so useless. So now we are going to introduce something that is containing more electron, okay, to make it become a negative type of silicon. So to do that, we need to replace one of these atoms that are pentavalent. Pentavalent means they have actually 5 electrons. Okay, they have actually 5 electrons. So 1, 2, 3, 4, 5. One extra one. So I have one extra electron. Don't know what to do with that. Okay, so that electron is going to be roaming around because the structure already stable with all the 4 electrons. So this one will be moving around. The free electron got more free electron now. So except this one, this is a hole. So maybe hole I use a red color dotted line. Okay, the hole. Now, example of material that we can use here is like arsenic or phosphorus. Okay, let's say we use phosphorus P. Okay, phosphorus P, and this one is boron B. Okay, example of pentavalent. Remember, trivalent is 3, pentavalent is 5. Pentavalent atoms are arsenic. Arsenic, you know, very poisonous. And I think this one is also, like, for example, phosphorus. Okay, and so on. Okay, so we use phosphorus here, just like we use boron in before that. So that means this silicon structure is going to have extra negative electrons roaming around inside there. Okay, so that means the characteristic now is the opposite. Characteristics of the N-type silicon. Okay, characteristic of N-type silicon. Number one, same thing. Our majority charge carrier are these electron, free electron. Okay, and then our minority charge carrier are these holes. Okay, holes. All right, so this is how we produce useful electron, useful semiconductor. We call the one the p-type and the n-type, and these two type of p-type and n-type, when they combine, they become the world's most important invention. Okay, it was actually discovered by 3 scientists which didn't go for their summer holiday, which they stay in the office, take out rubbish from the what we call it, from the rubbish bin. People throw away the discovery and then they take it out and study again. Finally, they discover something that we call the transistor. Later, then they discover diode. So diode is not the first one discovered or built. Transistor is the first one. After transistor, then they discover this diode. All right. So that's it for our semiconductor diodes. Okay, how we dope them, using what to dope them, and what is their majority and their minority carrier. This is our page number 5. Okay, page number 5, and the next one is our diodes. Okay, I will leave that one in the next video. All right.